go to the next presenter, Fatih Tarara. He is founder and managing director of MoJet Ltd. Fatih is a leading expert in fire safety engineering, tunnel ventilation, and computable fluid dynamics, with design, review, and operations experience in buildings and infrastructure worldwide. He is also the inventor of the MoJet tunnel ventilation system and has submitted over 20 patent applications in the field of mechanical engineering. He was the project director for the mechanical and electrical design of the new Tyne crossing, and undertook also quantitative fire risk assessments for the tunnel, which led to specification for the first fire suppression system with a road tunnel in the UK. Fatih has acted also as a technical advisor to the Land Transport Authorization of Singapore for a series of detailed fire suppression tests using low pressure deluge systems. So welcome, Fatih. Thank you for joining us. Yeah, you can take it from here, so you can take the controls.
Thank you, Miguel. That's very kind.
You're welcome.
Okay, so I will see if I can share my screen. Can you see my screen?
Yes.
Excellent. That's good. Okay, well, hello, everyone. So in my talk, I'd like to shift the emphasis from fire suppression to tunnel ventilation, because the idea is that the tunnel ventilation design should actually be treated quite differently when it's coupled with fire suppression. So what I'd like to do is to talk about how designers should actually approach this issue of tunnel ventilation design when fire suppression is applied. So I'd like to go through the general design requirements for tunnel ventilation, and then hone in specifically about the issue of longitudinal tunnel ventilation, and then move on to talk about tunnel ventilation with fire suppression. What I'd then like to do is to talk about a specific design example, and then show you a little bit about jet fan technology and how that's progressing, and then move on to some conclusions and your questions. So, generally speaking, in terms of tunnel ventilation, there's two major issues we need to watch out for. The first issue is air quality, and with regards to air quality, typically carbon monoxide, nitrogen oxides, and visibility are the key criteria. And in order to assess those in a road tunnel, we need to focus on worst case scenarios, i.e. congested, slow moving, or indeed stopped traffic. But actually, for most of road tunnel designs, we find that smoke ventilation is the defining design scenario, because that actually requires more ventilation. So for smoke ventilation, what we need to do is to control the movement of smoke so that we can allow the safe evacuation of motorists and allow also firefighting in the other direction. So here is a typical example. So you've got one tunnel that's actually an incident tunnel. There's a fire in it. And what we need to make sure is that the non-incident tunnel is pressurized so that if we're going through the cross passages, that the non-incident bore is protected. And we need to make sure that the smoke in the incident bore is actually pushed away from the escaping motorists. So that's a typical example of smoke ventilation application. So let's hone in a little bit more deeply with regards to longitudinal tunnel ventilation. I mean, what I've done here is just put up a picture of longitudinal tunnel ventilation using jet fans. I'm sure a lot of you are familiar with that, but we're going to launch a poll in a second and find out how many of you are familiar with this. But generally, in terms of longitudinal tunnel ventilation, there's three types. There's jet fans, there's Staccato nozzles, and there's also push-pull with shafts. Now, of those three, generally speaking, jet fans are the most cost-effective for relatively short road tunnels of 3 kilometers long or less. Although I am very aware that, for example, the Fehmarnbelt tunnel, which is around 18 kilometers long, is being ventilated with jet fans as well. So you can ventilate much longer tunnels using jet fans as well. So let's launch our little poll and find out a little bit about your knowledge of and your application of tunnel ventilation. Let's see if this works. Let's have a look. 1 second. So I have launched the poll, and if you could perhaps respond in the next minute or so as we are speaking, that would be very good. So if you could tell us about your experience of tunnel ventilation. Okay, that's very interesting. I can see the results coming through, and they're pretty clear. Yes, please carry on. Okay, that's very interesting. More results coming through. That's excellent. Yes. Okay. Okay, that's very interesting, and it's sort of the results I'm seeing confirms what I think is the case. All right, good. Well, okay, thank you to everyone. I will see if I can. I will now close the poll and share it. Okay. So I hope you can see the poll results. So yes, most of you have got experience or are working with longitudinal ventilation with jet fans, a few with Cicado nozzles, a small percentage with semi-transverse, and even less with fully transverse, and quite a substantial number of you not working with ventilation at all. Okay, so let's hide that. Good. So for the longitudinal tunnel ventilation, what we generally need to do is to make sure that we are delivering sufficient air to control the smoke. So the top image shows you what happens if we are not controlling the smoke properly, which is that the smoke can actually move in both directions, which is highly undesirable because you can have motorists trapped on one or both sides. If we generate sufficient airflow to control the smoke, then we're applying an airflow greater than the critical velocity, and therefore we can make sure that the evacuation can proceed safely upstream of the fire. Now, this criterion actually applies to the main tunnel, and it also applies to any open cross passages that may be subject to ingress by smoke. So what do we tunnel designers have to do? Well, first of all, we have to define the design fire, whatever it is, whether it be an HEV fire in excess of 100 megawatts or just a, let's say, a car fire of no more than 5 megawatts. We then have to define the operational scenarios, exactly how is the traffic moving in that case, because that's important in terms of us delivering the correct ventilation response. And then, of course, then we've got to work out what the required air velocity should be for smoke control. And then, of course, work out what the so-called hot case conditions are. By hot case, I mean the cases under fire. And then the bit that we also have to do, which is quite important, is also calculate the so-called cold case conditions. And this is the case without any fire. So this is the difference between the cases. The hot case is basically what happens if everything goes wrong. Okay, so we've got a fire, we've got wind that's blowing the wrong way, we've got open cross passage doors, none of the fans, the redundant fans are operating. And in that case, let's check whether the critical velocity for smoke control is achieved. In the cold case, everything goes our way. There's no fire or very small fire, there's a favorable wind, etc., etc. The cross passages are closed and all the fans operate. And in that case, we just need to make sure that we're not blowing the people away, literally. So we've got to make sure that the air velocities exceed 10 meters per second or not. Now, if there is a fire, we've got to make sure that we've got sufficient redundancy in case the fans are destroyed. So this is a typical example of a UK standard in terms of assuming how many fans are destroyed. But this, of course, relates to the situation without fire suppression. And in case there is no fire suppression, typically the requirement is that we should allow 10% or more jet fans for maintenance and a number of fans destroyed as per the table above. So we do need to add quite a bit more fans on top of what we calculate through, for example, our thrust calculations. Now, it's quite important to think about how the traffic is actually going to move, because that affects exactly how we operate the ventilation system, if we even operate it at all. And of course, the other thing to remember is that it may not be simply a question of fire and forget. We may need to have some feedback control of the ventilation system as well to make sure that the velocities are within the correct range. I'm a committee member of the World Road Association, PRC, and PRC has issued some guidance about this. So there are a number of cases to be considered. The first one is unidirectional traffic without traffic congestion. And in that case, the situation is quite clear. We've got to generate flow velocities to minimize the back layering of smoke. But if you have got unidirectional traffic with traffic congestion, the situation changes slightly, because instead of generating the velocity for smoke control, we should actually go for something slightly less, something like 1.2 meters per second, just to minimize the flow of smoke upstream. Because don't forget, in this case, you may have traffic on both sides of your incident. And lastly, if you have bidirectional traffic, again, we should generate only low flow velocities, except for certain circumstances, for example, to avoid flow reversal. And if you are looking at the various countries, they do actually advise different approaches, which may again be different from the approach from the World Road Association. So, for example, the feedback control system is required in a certain number of European countries, including Switzerland and Austria, but not in the UK. And in Austria, for example, the air velocities required in unidirectional traffic flow are fixed. So there's no reference to critical velocity for smoke control in Austria. If you're in Germany, then there is a reference to the critical velocity for smoke control without congestion through the German RAPT regulations. So everything I've spoken to you up to now is the situation essentially without fire suppression. So how does the situation change with fire suppression? Well, there are three main issues to think about. First of all, how does the critical velocity for smoke control change on the basis of fire suppression? Well, the first thing is obviously the total fire heat release rate is reduced via fire suppression, as mentioned to you by Johnny earlier. And of course, the convective proportion of that fire heat release rate is also reduced via fire suppression. So we are given a double helping, if you like, of goodness with the fire suppression. So not only is the fire heat release rate reduced, but also the convective proportion of that fire heat release rate is also reduced. So that's all very good. In addition, the density of the air downstream of the fire is increased because it's cooled down. So any jet fans downstream of the fire, their thrust is enhanced. The other issue is, you may recall that I mentioned fire-induced damage of the jet fans. Well, in this case, that damage may be reduced because instead of having, for example, 2 banks of jet fans being destroyed, you may only have 1 bank, the bank that's directly adjacent to the fire. And even that bank may not be entirely destroyed. But let's say for conservatism, it's the bank that's adjacent to the fire that's destroyed and no other. Now, let me go through a short design example with you so that you can actually see this in practice. So what you can see here is the RISE tunnel in Turkey, where we conducted a design exercise. And in that case, we were asked to estimate the critical velocities with the Untitled fire suppression system and to estimate the required number of jet fans. And in order to do that, we actually calculated this using IDA, which is a commercially available tunnel ventilation software. We modeled the tunnel as two bores, including all the slope and the fan locations, with each bore, the north and the south, being calculated independently. With fire situations, we assume that the fire backs up all the way to the entrance portal. For the jet fan thrust, here's the equation for the aerodynamic thrust for each jet fan. And we did assume a certain installation factor of 0.71 for a conventional jet fan. I will explain a little bit more about how that can be improved later. And the power consumption per jet fan was assumed to be 30 kilowatts. So in this case, we were told that the unsuppressed fire heat release rate for a heavy goods vehicle would be 100 megawatts. Now, with the activation of the fire suppression system, we assume that the heat release rate drops to 40 megawatts, which is more or less consistent with what you've seen from the test results shown by Johnny just a minute ago. But for conservatism, we assume that the suppressed fire heat release rate was 20 megawatts. And in fact, that is very conservative because indeed, the measurements showed that the suppressed fire heat release rate is actually a lot less than that, more in the range of 8 to 12 megawatts. And for these calculations, we had a very conservative assumption that the fans within 120 meters downstream and 30 meters upstream are destroyed. So we destroyed quite a bit of fire, quite a few fans here. Whereas in fact, as I mentioned to you before, you can argue that you're not going to destroy so many. And we looked at various fire locations, 7 of them in total. Now, if you think about the fire suppression system, and particularly the Untitled fire suppression system, how is it working? Well, it's working because we are inhibiting the pyrolysis, in other words, the conversion of the solid to gas, which can burn. We're inhibiting that. We're also smothering the combustion itself with liquid and water vapor. And we're also cooling the hot plume. This is important for the calculation of the critical velocity for smoke control. And lastly, but not leastly, we are preventing the fire spread because we're preventing the fire spread to the cooling of the neighboring surfaces. So in this case, we calculated the required number of jet fans. So for the left and the right tube, or the north and the south tubes. And as you can see, we didn't actually need a large number of fans on. The blue line is the number of fans that are operated for the various fire locations indicated here. So as you can see, we only needed about 12. And for the other tube, we actually only needed a maximum of 8 operational jet fans. Okay, and the other ones were actually switched off, which were initially set up. So the good news is, for this particular example, we actually reduced the number of required jet fans quite dramatically. For the north bore, from 50 down to 16. So that's the 12 I mentioned to you earlier, plus 4 additional jet fans for maintenance and fire damage. And for the south bore, we actually managed to reduce them also substantially from 40 down to 12. That's 8 plus 4 for maintenance and fire damage. Clearly, in your design, you've got to think about the probability of a delay in the activation of fire suppression or a failure in its operation. And that's why you need to get your motorist out of that fire situation as quickly as possible. A few words about jet fan technology. So what I've done here is just indicate a kind of a timeline for jet fan technology. So at the top, you can see the conventional jet fan that's been around for a long time, around 60 years or so. That's been followed by the technology of jet fans with deflectors, in this case on both sides. Around 25 years ago, we had the slanted silencer jet fans, and much more recently, the MoJets. So why this change of technology? Essentially, it's mostly about the Coanda effect. So what you can see here is a conventional jet fan discharging its jet. And what's happening is that the jet is sticking to the soffit, and that's causing some aerodynamic friction. And the friction clearly is against the flow direction. And unfortunately, we do lose typically 30 to 50% of the thrust via aerodynamic friction. So the solution is clearly to deflect the discharge jet and to reduce the aerodynamic friction. And if we do that, we can actually increase the internal thrust by up to 100%, which is of course a great thing to do. In order to select the right technology, you've got to ask yourself the question, well, is the technology giving me this jet deflection? Is it compact? Does it extend my throw? That means that if the throw of the jet is too long, it may actually attach either to, for example, to signs or to the floor of the tunnel or to heavy goods vehicles. In other words, not a very good idea. Does it regenerate some noise, the deflection technology itself? Does it induce any metal fatigue risk? Does it generate an additional power consumption requirement? Does it lose bench thrust? And does it create a risk of bearing damage through separation, flow separation? So here's a little table of comparison between the technologies. So you can see actually the top line, which is the conventional technology, is actually great. It's got green everywhere, except it doesn't actually deflect the jet. The deflector technology does deflect the jet, and it is compact, but it actually loses out on most of the other criteria. Slanted silencers also deflect the jet, but they're not compact. They require additional power, they lose bench thrust, and there is a risk of bearing damage. And the MoJet does tick all the right boxes, as you can see. Now, the way you get the benefit depends on where you actually install your fans. So if you install the fans in the corner, you can actually halve the number of active conventional jet fans you require. This is based upon measurement tests that we undertook. But of course, you do need an allowance for maintenance and fire damage. The other advantage is that you can actually reduce the spacing between the MoJets down to about 40 meters or so, with less cabling required, of course. For soffit mounted MoJets, typically you require around 25% fewer MoJets compared to a conventional jet fan. Now, if you combine the two, if you combine the MoJets and the TunProtect fire suppression system, then you have a double whammy. You can actually reduce the number of fans by at least 50%, but I will show you an example just now. But you do need to check the allowance for fans on the maintenance. And it may well be that after all these reductions, that actually it's the traffic congestion case that becomes your defining criterion. So you do need to check that. So in the rise tunnel for the South Bore, we started off with 40 conventional jet fans with no fire suppression. Then we moved on to 12 with TunProtect. and that can be reduced further to only 8 with the MoJet and TemperTech. So you can get a huge benefit out of that. There is a handout available on your screen where you can actually download information about this presentation and also about MoJet. So thank you very much, and I look forward to your questions.